Hello everyone, my name is Iman and today I want to talk about blockchain smart contract security or the B-side Calgary. And this is the outline of the talk. And first we will talk about what is blockchain and we will talk about smart contracts. And then we will talk about the importance of the DeFi and NFTs. And, the smart contract security is important. We will investigate why. And then we will discuss solidity problems. And other than that, the main focus of this talk is on smart contract security issues. While I'm talking about different issues, I will talk about the secure design patterns also. And then I'm going to conclude the talk, and then we will have a Q&A. Who am I? My name is Iman Sharafaldin, and I'm an application security lead at Forward Security. Also, I'm a PhD candidate in computer science, and I have published like dozens of papers, and I have like more than 1,000 citations. And my main topic my main interest was cybersecurity or is cybersecurity, and other than that, those papers that you can see that are highly cited are related to intrusion detection and visualization. Other than that, I was involved in some projects that were related to smart contract security. What is blockchain? Blockchain actually is a chain of blocks. You can consider that as a chain of blocks, and each block can contain some transactions. You can consider it as a book or as a notebook, and each page could be a block, and you can write some imaginary transaction inside that. Like, I don't know, Iman has sent some Ether or some Bitcoin to Alex, and etc. And each page is a block, and the whole thing is a ledger or blockchain. And why it is very revolutionary? The main reason is that for the first time in history, we don't need a third party to transfer value from person A to person B, thanks to the algorithms that we're using and in the blockchain environment. What is a smart contract? A smart contracts are agreements that have been codified inside blockchain. And here, when we talk about smart contracts in this talk, we're talking about some Solidity codes that are running on the Ethereum network. And they have some main characteristics. Some of them are censorship resistance, being immutable, and being decentralized. And the reason that the smart contracts are revolutionary is that these are all the reasons. Like, for example, censorship resistant. Let's assume that we want to run a lottery website, and tomorrow maybe government can come after us and bring down the website and actually arrest us or something like that, and stop the backend, and the site will never work again. But you can easily write the smart contract code to implement this lottery application. And let's assume that this is a simple lottery, like anyone can send some Ether to that address, which is a smart contract. And at, I don't know, 6 p.m. every day, the smart contract would select a random person and deposit all the Ethereum to that address and just deduct a small percentage of the fee. And after that, no one can stop that if, for example, the developer didn't provide any stop function for that. Even the developer cannot stop that, let alone the government. And this is, I'm not talking about like criminal aspects, but this is something beautiful. We can run a code that no one can stop it, and because it is running on a decentralized way. And other than that, we can talk about decentralized finance or DeFi. And, this is a huge thing, DeFi. and it is disruptor of financial intermediaries. And I believe in 5 to 10 years, in the next 5 to 10 years, we don't need bank anymore. We don't need any banks anymore. And the reason is that in a cashless society, a smart contract can do everything for us without any need to any human or something like that. This could be fully automated. And DeFi is a very young sector. And first I remember like 1.5 years ago or 2 years ago, like the transaction in DeFi or the total value locked in DeFi was less than $1 million. And now when I'm talking today about DeFi, it is more than 50 billion. I mean, the value that is locked in DeFi projects is more than $50 billion. And here is an example, a real world application of a smart contract. The name is AAV or Aave. And you can see that you can deposit your here, for example, you can see USDT, USD coin. These are stable coins. These are some tokens that can be like on an Ethereum network or a Tron network or something like that. And each token represents a US dollar. And because of that, it is stable. And you can deposit your money into those into those DeFi smart contracts here of it, and also you can borrow money, and you can see all the rates here. The next interesting topic that the smart contracts is the reason that we have that is NFT or non-fungible tokens. And NFT is all about tokenizing assets on the blockchain. And when we are talking about non-fungible, for example, Bitcoin is fungible. It means that if I have one Bitcoin and if you have one Bitcoin, these Bitcoins, the values are the same. I mean, for example, if we want to sell it, if the price today is, I don't know, 50K or 60K, then they will pay 50K or 60K to you and also to me. But for non-fungible tokens, there are tokens on a smart contract that is running, for example, on Ethereum blockchain. And each token has different value. And maybe you ask yourself, what are those cats that I put on my slides? And here, actually, these are CryptoKitties cats, like one of the pioneers of NFTs. We have a very awesome company here in Vancouver called Dapper Labs that they have outstanding job and a world-class job, and they launched two products. One is CryptoKitty that is launched a few years ago, and the other is NBA Top Shot, and both of them are NFT projects. And you can see some of those cats, they have been sold for crazy amount of money, like more than 100K, and you can breed the cats together, and these are on blockchain. The images are not on blockchain. I mean, the attributes of the cats are on the blockchain, and based on the attributes, the image can be generated. And here, actually, you can see another project called NBA Top Shot, and this is actually my account on NBA Top Shot. I put like a couple of $100 into that, and now after 6-7 months, that $200 or $300 is worth more than 50K actually. And for example, here you can see a moment of LeBron James playing basketball, and someone has paid 70K for that moment. And this is the beauty of NFT. NFT can conquer different worlds, such as art world and collectible worlds. And this is a super nice thing that we have, and this is one of the applications of a smart contract in the real world. And why smart contract security is important? Every week or every month or sometimes every day we hear like a news or attack and those amounts are crazy. Like There are millions of reasons that we should secure smart contracts. We can see like Binance Smart Chain DeFi. This happened recently, and they lost $31 million. And you can see all the news around the world. And I believe, these vulnerabilities, the heists are bigger than the real world heists. And this is crazy because there are some small problems in those smart contracts, and those problems can bring us a huge disaster. And in this talk, we are going to talk about all those problems, all the important ones, actually. Solidity actually is a language, is an object-oriented language, and that you can use that to develop the smart contracts. Solidity was initially proposed by Solidity was initially initially proposed in August 2014, and the language is similar to Java and JavaScript. I wish I could say that it's a beautiful language, but it's a messy and bug-prone language. And one of the reasons that we have so many hacks is the limitation that the limitations that we have in this language, and it has like a different object type that we have in like common languages, such as integer, string, hash map, and all those stuff. And Ethereum transaction, actually, if you want to talk about like Ethereum transaction, each transaction has some attributes. I'm gonna go over some of those attributes. Nonce is a number that determines how many transactions were broadcasted by the sender before this transaction. And it uniquely identifies the order of transactions sent by the same sender, and it is used to avoid repeated execution of transactions. Other than that, gas price is related to the concept of gas. Gas is a virtual currency unit that the sender needs to pay for executing a transaction that modifies the state of the blockchain. Every instruction in the EVM specifies how much gas the user has to pay for its execution. Gas price then determines how much Ether the user is willing to pay for one gas. This can be any non-negative number, including zero. The total price of the transaction in Ether is then determined by multiplying the gas price by the cost of all executed instructions. Data is an optional string of bytes that encodes the smart contract method called by this transaction and the arguments passed to the call. Value is an optional number that determines how much Ether is sent along with this transaction. Chain ID is a constant numeric identifier of the Ethereum network that allows for distinguishing the network type. For example, ETH, ETC, and the chain ID of ETH is 1. V, R, and S, actually, there are cryptographic values that determine the transaction signature. From these ones, one can derive the public key of the sender, and from the public key, one can generate the Ethereum address of the sender. 2 actually is the address in the Ethereum network that determines the recipient of the transaction. If the purpose of the transaction is creating a new smart contract, the recipient is a special address, which is 0. Another special recipient is the address 0xDET that is used for burning Ether. And gas limit also is related to the fact that how much gas you want to pay for that transaction. We set the maximum gas. Here are the main smart contract security issues. The list might not be complete, but these are the main ones and are the important ones. And we're gonna go through all of them: arithmetic bugs, Intransi attack, race conditions, exception handling, weak random generator, and the next two ones are related to timestamp dependency and transaction ordering dependence and front running. And the next one is related to the problems in the library design flow, a zero initial balance assumption and denial of service. And the arithmetic bug, actually, we have this problem in like common languages. Let's assume that we have a car with an odometer, and let's assume that it has just 6 digits. And if we drive around 1 million kilometer or mile here based on the odometer, then we will have like an overflow. And here you can see a function decrease allowance in solidity. And this is vulnerable actually because about this function, we're going to talk about that on the next slide when we are talking about ERC20s. But if, for example, the victim set an allowance for other guy or an attacker as 15, and if the attacker convinces the user or the victim to reduce it to 16, then the amount of allowance that the attacker has actually it's a privilege to withdraw Ether from another account. It would be like a huge number, and the attacker can withdraw all the Ether that the victim has. And this is actually, we're going to talk about that. But we have this is an integer underflow. We have integer overflow. We have integer underflow. And the way that we can protect our code against these kinds of attack is we can check the results of arithmetic operations for the valid operation. And other than that, we should use OpenZollin framework, and there is a library called SafeMass. We can use that to avoid these problems because the library actually can check the validity of the results and can avoid those situations for us. Intransi Attack is another attack that it's one of the famous one, and decentralized autonomous organization or DAO was like a smart contract that was very famous in 2016, and the attacker was able to withdraw 3.6 billion Ether. Like with the today's value of Ether, it is billions of dollars. But that was the reason that we had a fork back then. Actually, we had the fork, the smart, Ethereum Classic and the Ethereum that we have right now. And the way it works is that you can see, the Intransi Attack. You can see the diagram here. And the attacker, first, what is reentrancy? Reentrancy by itself is not an attack. It's like a definition. Let's assume you want to send an email to your friend, and in between, you can put the email as a draft and go and send an email to another friend and come back and write or complete or finish the email for the first friend and send that to the first friend. This called reentrancy, in computer science. But let's assume that we have a vulnerable bank application that allows reentrancy, and but the problem is that before it changed the states after the sending the balance to the users, and that is the problematic situation that we could have. Here we can see the same problem in like a smart contract. The attacker can write a malicious proxy smart contract, and here we have withdraw balance, that you can withdraw the amount of money that you have already deposited to the DAO smart contract. And here we have a function called fallback in Ethereum smart contracts. The fallback function is you can consider it such as it is like an event in JavaScript or something like that. Whenever a smart contract receives any ether, the fallback function would be called. And the way it works is that the malicious proxy smart contract calls the initiates the withdrawal, and in this function, the DAO actually starts to withdraw the balance, and then it starts to transfer the ether back to the malicious smart contract. And in the fallback, actually, you can see that uh, we have another recursive call, which is like a loop right now, and we call the withdraw balance again. But the problem here is that uh, the developer forgot to update balance before sending the ether, and because of that, still the user has some balance, even though we have already sent some ether to the user or the attacker. And because of that, we can have a loop here, and then, for example, it could have a condition, and after the condition has been met, we can stop, and they can still near all Ethereum that this smart contract has actually. And after that, it starts to update balance, but already the money has gone. And you can see, there are different methods that we can avoid that. This is like a serious problem in smart contracts. We had many smart contracts with reentrancy problem. And one of the methods is that never ever update the state of blockchain after you're sending anything. You're calling the send method. I mean, we have different methods to send value to another smart contract or another address. We're going to talk about that. And the other way that we can avoid that is that here the problem was that the developer was using address.call.value function. And because of, you can see these functions, we have these three functions: send, transfer, and address.call.value. And you can see this has adjustable gas. It means that, as long as you have gas, if you don't set any limit for that, it can, execute this loop or these recursive calls actually. And the developer at least could set some limits here. Or if the developer was using these two, address send and address transfer, because this fallback has some code inside that it requires more gas, and these functions would fail, and then the attacker was not able to attack actually. And other than that, you can see different behavior on the error. In case that we have any error, these two functions return false, but these functions, this address.transfer returns an exception, and this exception actually reverses the transaction. We have also race conditions in ERC20 tokens, and the reason is that we cannot synchronize the states in Ethereum blockchain. And what is ERC20? I believe you have heard names of different tokens on ERC20. I mean, on the Ethereum blockchain, we have many, such as VET, or prior to that, BNB was even on the ERC token, was an ERC token. Right now, it has its own mainnet. The way it works is that ERC is Ethereum request for comments, and these are like RFCs in network. And ERC20 is an interface that if you implement that, you can easily create your own token under 5 minutes. I don't know, like forward sec token or forward sec coin, anything that you want. And that interface, to implement the interface, there are different functions. And here you can see one of the functions is approve. And the approve function actually, if like anyone, for example, if I have an Ethereum address, if I approve like any value and any other address, that address can withdraw that value out of my account actually. And here we have Alice and Mallory. And as you can see, Alice set the, let's assume that Mallory is is a developer that is working in another country. And Alice wants to pay her 10 tokens and set the allowance of the Mallory to 10. And then actually uh, Mallory convinces the Alice that you should set it 15 because I've done more and you should pay me more. And maybe Mallory wanted to do that, and she can set like the approve to 15. And but Mallory can use a race condition scenario here and withdraw 10 token immediately before Alice calls the approve function, and then Mallory can again call transfer from function and withdraw 15 more tokens. And now the Mallory was able to withdraw 25 tokens instead of 10 tokens, or even like after that 15 tokens. And this is like a classic race condition scenario in ERC20s. And the ways that we can stop this is that these are the two recommended ways. We can reset the allowance to 0, or we can implement safe methods for increasing and decreasing the allowance, and that can help us. That can help us actually. Exception handling. This is another scenario. We have, we had a King of Ether smart contract, which was a Ponzi scheme, and the way it was working was that, at each moment we could have one king, and anyone could be the king, and the king would own the pot. And in order to be the king, you should send more ether than the previous person. Other than that, one of the rules in the game was that when we are changing the king, for example, first user could send 1 ether to this smart contract, to this Ponzi scheme, and the smart contract could set him as like a new king. And the second user, in order to be the king, could deposit 2 ether. And then, in order to alleviate the pain of this first user, the smart contract would compensate some amount of money back to him and would set the user to as a new king. But here is the catch. In their code, they didn't check for the exceptions that could happen. And the exceptions we were talking about, that if, for example, we use that send function, then if the smart contract, let's assume that this second user is not a real user, as it is using a proxy smart contract, then in the fallback function, this user can put some malicious code or even some other code. And then let's assume that King of Ether is using that send function, because now it should execute that fallback, and it doesn't have enough gas, then it will fail. But they were not checking that it is failing or not. Then the user one would not be compensated, and there would be that is a loss for user one. And the other problem was that user two would be the new king. There would be no problem, but the owner of the smart contract would own the compensation amount of the user one, which is not fair. Then the owner of the smart contract would be this attacker that you can see here, because he can, he has some profit that he can make here. And always we need to check for exceptions and handle the exceptions correctly when we actually encounter these situations. The other problem that we see in smart contracts is that now the problem is that we don't have a real random number generator, and we have a pseudo random number generator, and the seed. The other problem is that the seed could be predictable, and that is a huge problem because if we want to base our decision on the on-chain data, such as block number or block ID or I don't know the timestamp, all of them are predictable and can be seen by attacker. And here we have a lottery smart contract, as you can see, and the victim actually can deposit some ether, and the attacker is the owner of this smart contract also, and the attacker also can deposit some ether. Now the owner of the smart contract can call a function which is called like the function name is choose the lucky one. And whenever, like in a normal world, whenever the owner call this smart contract, this smart contract function, then without any problem, one of the users could be randomly selected and can have all the money. But in this scenario, the attacker can write a smart contract as a proxy smart contract and deposit ether using that one. And the attacker is also the owner of the smart contract, can have a loop here and evaluate the random condition, timestamp or the block number, or anything like that. And whenever it was in his favor, he could call the choose the lucky one function, and he can have all the money. And this is a huge issue actually. And the way that we can avoid that is we can use a secure random generator in using one of the oracles such as Chainlink. Chainlink has VRF, verifiable random function, and then we can be safe actually. And the oracles, they're providing data from off-chain to on-chain, and they're very useful and practical. And the other problem with the smart contracts is like some of the smart contracts is dependent on the timestamps, and this is bad actually. And the reason that this is bad is that the miner can set the timestamp. The miner cannot set like an outrageous timestamp that he wants, but there is like a 15 seconds toleration there. And let's assume that we have a Ponzi smart contract that anyone can invest some ether inside that. And the way that it works is that the last person who has invested in that smart contract would own the pot. But it needs like 30 seconds to, and after 30 seconds, if no one sends any ether to this smart contract, then the owner can withdraw all the pots. And here, the malicious miner can wait for for one exact moment that, for example, for 15 seconds, no one has sent anything, but they have, I don't know, 30 seconds. And then the malicious miner can set the timestamp to a specific timestamp and win their smart contract, actually. Reset the investments and then deposit the ether. Actually, the function reset the investments can be called by the owner of the pot, and after that, it's easy to retrieve all the ether that it is in this smart contract. And transaction ordering dependence and front running is another problem. The other problem is that developers, they assume that like the order transactions order are fixed and cannot be manipulated. But in fact, whenever the transaction works in this way, that you can sign a transaction and send it to the nodes, and there would be a mempool, and all transactions are there. And the miner, when the miner finds a block or mines a block, then the miner can reorder the transactions in any way that he wants. And let's assume that we have a puzzle solver smart contract that, for example, I don't know, a very specific problem in physics or science, and when everyone are challenged to solve this to retrieve some ether, and the victim is like a smart guy, he submits the solution to this smart contract, and here the miner, let's assume the miner finds the block or wants to mine the block, and now the miner can see all the transactions in mempool and can see the value that the victim has submitted and can check that the value is correct, and then reorder the transactions and put his transactions in front of victim transaction and retrieves the reward. Because of that, we shouldn't depend on the orders of the transaction, and we should take care of that. The other problem is that library design flaws, and valid library is one of the one of the vulnerable smart contracts that we had. And the way it works is that we can use different libraries on the Ethereum blockchain, but the problem is that whenever a library has a problem and we are using that library, the problem is that we are trusting that library, and because smart contracts are immutable, we cannot use another version of that library, and then our smart contract would be vulnerable. Here, actually, the problem was that uh, the developers of this smart contract, they forgot to init the wallet, and someone else actually, and the people were using this smart contract, and the init wallet was executing in the context of those smart contracts, not the context of the father or parent smart contract. And after that, someone finds that and called the init wallet and changed himself to owner. And after that, he killed the smart contract. You can actually destroy a smart contract from blockchain by calling a specific function. And the problem here was that if you kill a blockchain or terminate not kill a blockchain, kill a smart contract or terminate a smart contract, after that actually no one can find that the smart contract, that library that we are using, and all those smart contracts that are using this library are frozen after that. And this is a huge problem, and right now there are hundreds of thousands of ether are locked due to these kinds of bugs actually. And the other thing is that we should never assume that we have a zero initial balance, and this is a simple fallback function, and as you can see, it's payable. And as you can see, like here we have a require. It's like an assertion that checks amount raised is more than this balance, and then it continues. The developer doesn't know that. The developer assumes that whenever we send ether to a smart contract, this function would be called for 100%. But this is not true. There are some cases that this function, this fallback, would not be called. One of them is when a miner mines a block, the miner can send ether to a smart contract, then this function would not be executed. The other way is that whenever we want to terminate a smart contract, we can send the remaining amount to another smart contract, and that is the other way, that if we use that method, this fallback would not be executed. This might not be a huge issue, but please always know that it is possible that you send, and you can send some ether to a smart contract without fallback being called. Denial of service, we have two main types of denial of service. The first one is exceeding block gas limit, and the second one is a transaction revert. Let's assume that we have a smart contract that now we have selected like a winner or something like that, and now we need to refund the remaining balance to the owners of those balance. And here you can see there is a loop. There is no problem if you see the loop, like it starts, it goes through all the addresses and start to transfer the value and to those addresses, the remaining balance that they have. But the problem arises when, for example, for 100 user there is no problem, or 1,000 user. But let's assume that, I don't know, 10,000 users or 20,000 users are involved in this smart contract, and each instruction that is running in this code costs us money, and even each block has a limitation of like the gas fee. Like I don't know, we cannot have more than 12 million gas or something, or 15 million. There's a limit that they update every year, and let's assume we have that amount of users that uh, we go over the limitation of the block. Then we could never execute this function, and it will stuck forever here. And this is a very bad design pattern, actually. You shouldn't use this pattern. You should use this pattern. Sorry, I actually put all the images in this one slide. But you shouldn't use this pattern because this is very costly. And on the other hand, you should use this pattern. And each person should be responsible to claim the refund. And now we don't need any loop, and then there will be no problem. The other problem with this pattern is that we could have some malicious guy that send us some like Ether, and he can use like a proxy smart contract. And as you can see, he can put like a revert in function in that smart contract. And whenever we want to refund the remaining balance, forever we will stuck because always the transaction would be revert. But this pattern saves us. And secure design pattern, actually, these are some tips and tricks. For example, we should check all preconditions before any calls to external smart contracts and updated state variables before the call. We should use require to validate inputs because require refunds all the remaining gas. We should make all important function possible because in case of any attack or any problem, we should be able to pause that function. And we should use safe masks to avoid integer overflows and underflows. We should avoid using timestamps in conditionals. And also, we should check the results of any call, send, or transfer because of the reasons that I was talking about, the exception handling slide. And we should always choose the most strict modifiers allowable. And other than that, this is good that we can always, out of all those attacks that we have seen, many of them, the attacker was using a proxy smart contract. One of the best ways to avoid the smart contracts call our smart contract. You can see one way, which you shouldn't use this way because it will fail in some cases. And we have a function check for human here. We can check the size of code of the address. That address, the smart contract addresses, they have some code because of that, but like human addresses, they don't have code. Because of that, there should be some value. But there is one case that can bypass this, and if a smart contract call another function inside the constructor, then it will fail actually. And this method is not good. But the proven method is this one. We should put like require message.sender equal to tx origin. And tx origin is the person who has initiated the transaction, and if the sender is equal to the TX origin, it means that it's not a smart contract. But the problem is that when we do such a stuff, then we cannot have multi-sig wallets, and they would fail because multi-sig wallets is not supported natively by Ethereum, and we need some smart contracts to happen. In conclusion, I believe the smart contracts are going to change the future, and also DeFi and NFTs are so big, and they're gonna change our world forever. And it is completely visible that if there is a bug in a smart contract that is handling a DeFi protocol or an NFT project, it can be devastating. And other than that, I believe currently developers are not trained very well to code securely, and that is one of the reasons that we can see a lot of hacks around and a lot of money is being stolen, actually. And these are my references. Other than that, I'm ready to answer the questions. Okay, let me please share my screen back here. Okay. I can see a few questions here. First of all, the last question is that how can we prevent complex reintransi attacks such as cross-function reintransi attacks? The thing is that OpenZeppelin, it has provided, you need to use mutexes, and there is something called reintransi guard, and there is a modifier called non-reentrant. You can use that to define your function, and that by using that you can prevent that. And the other question, SafeMass, actually SafeMass is for OpenZeppelin, but the thing is that from Solidity version 0.8, they have integrated that SafeMass inside the Solidity, and because of that we can have fewer problems. And before going for the next question, actually you can see our carriers mentorship page on the background, and you can join us. We have a cool company called Forward Security, and we have some positions for you, and you can find the website there actually. And other than that, Ralph has asked that how we can identify Ponzi schemes. Those are not cryptocurrencies, those are some smart contracts, and by reading their code it's obvious, but prior to that, they're gonna advertise themselves as like a Ponzi scheme. And other than that, what other languages are used for smart contracts aside from Solidity? C and C++ and Rust. These are the other languages. On other, it depends on the blockchain. For example, for Solana, you can code using C or Rust, and but also for Polkadot, you can use Rust. And other than that, for Cardano, you can use Haskell. But I haven't seen anything with Java. But yeah, other than Solidity, Rust is the second language that you can use actually. And what is a dApp? dApp is like a distributed application that is running over like Ethereum or any other blockchain that is supporting smart contracts. And majority of them are a smart contract that is running on that blockchain. And this is it. Thank you very much, guys, and have a nice day. Bye.